let's go ahead and talk about the integrating factor stuff. So I'll remind you and the folks at home that last time we solved this differential equation, y prime minus 3x squared times y equal to x squared, using separation of variables. So we brought everything to the right-hand side. We observed that we could essentially separate the x's from the y's, right? We could multiply x squared times 3y plus 1. Then we brought the x's to the right, the y's to the left. We integrated both sides. We did all the solving stuff. And we finally ended up with the solution of y equal to a constant times e to the x cubed minus 1/3. Just as a reminder. And so now what we're going to do, now what we're going to do is we're going to solve this same differential equation using first order linear. Now, it's not always an option to do one or the other. This differential equation happens to be one that can be both separated and solved using first order linear. It's definitely first order linear because we can see that it's first order, you've only got a first derivative, and it's linear in y, you only have a y to the first. Those are the hallmarks of being first order linear. If you have like a y squared, it's kind of out of the question to solve for or using the integrating factor. So that's kind of, in fact, if someone was asking like, is this separable or is it first order linear? If you see y to any power other than first, you're pretty sure it's not first order linear, and it's probably going to have to be separable. But let's look at solving this first order linear differential equation, y prime minus 3x squared y equal to x squared, using the integrating factor. So to be able to do this, we have to be able to write our differential equation in the following format. So the format for I'm going to abbreviate this from now on, but I'll write it out this time. For a first order linear differential equation, from now on abbreviated as FOLDE, is y prime plus a function of x, or whatever your other variable is, right? Whatever your independent variable is. It's often also a function of t, times y to the first equals some other function of x. So sometimes something will be a first order linear differential equation, but it won't start off in the exact format we need it in. And we'll see a few examples of that. This one definitely can be written this way, but we need to observe that this needs to be plus right here. So we should really think of this as y prime plus negative 3x squared times y equal to x squared. And we're going to observe or note that this negative 3x squared is our p of x, and this x squared is our q of x. So then we're going to do the thing which makes it kind of work, which is we're going to find the integrating factor. And the reason it's called the integrating factor is because it's going to allow us to essentially view the left-hand side as the derivative of something, and then it's going to make it easy to anti-differentiate or integrate both sides. So our integrating factor, and did he call it mu of x or I of x? It's actually mu. He might have said u. I doubt it. He probably said mu. It's a Greek. Really interesting. So in most textbooks, it's usually mu of x, which looks a lot like a u. It's the Greek letter mu. So the integrating factor mu of x is e to the integral of p of x dx. And usually we're pretty loose with this integral here. Like if this integral ends up being a natural log of the absolute value of x, we kind of ignore the absolute value part. We ignore anything that kind of makes it weird. So like we don't write a plus c, we don't do anything weird. We just kind of do it as straightforwardly as possible. So in this particular case, our integrating factor mu of x is going to be e to the integral of negative 3x squared dx, which is going to be e to the negative x cubed, no plus c required. So then the idea is we're going to multiply each piece, or I really would say both sides of this equation. I really think of it as multiplying each of the 1, 2, 3 pieces by this integrating factor. So we're going to say that, let's see, yeah, I'll just write, I'm trying to think about the way I want to write it. I'm going to write this as y prime times e to the negative x cubed plus y times e to the negative x cubed times negative 3x squared is equal to e to the negative x cubed times x squared. So I've just multiplied everything by mu of x. And now here's the reason why we did this. And it's going to work this way every single time. After you've multiplied both sides by mu of x, this left-hand side is the derivative of a product. And it's actually really, really easy to tell what product it's the derivative of. Take this y prime times mu of x piece and drop the prime. So all of this here is the derivative of y times e to the negative x cubed. We can check, right? If we do the derivative over there, right, let's do it over here. If I take the derivative with respect to x of y times e to the negative x cubed, well, product rule says it's the derivative of the first part times the second part plus the first part y times the derivative of the second part. Well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And look, that's exactly what we have over here. And it always works this way. So whenever you do this, you automatically say, oh, that left-hand side is just the derivative of y times whatever your integrating factor is. And then the right-hand side is still what it was. It's e to the negative x cubed times x squared. Now, if the derivative of all this stuff is equal to e to the negative x cubed times x squared, then we can say that y times e to the negative x cubed is equal to the antiderivative of e to the negative x cubed times x squared. And then we have to integrate this. Now, sometimes integrating this is going to be relatively straightforward. Sometimes it's going to actually be impossible. You might get an answer where y is equal to some function that we don't actually know how to anti-differentiate, which is atypical, but is fine if it happens. Here, we can definitely solve this by doing a u substitution. If we let u, in fact, yeah, no, I'll just do it. I mean, we can kind of see what it's going to be already, because we took the derivative e to the negative x cubed and got e to the negative x cubed times negative 3x squared. That's almost exactly the same as this. We're just off by a factor of negative 3. But to show the work, we would say u is equal to negative x cubed. Du is negative 3x squared dx. I would divide both sides by negative 3 and say negative 1/3 du is equal to x squared dx. So that then this integral becomes the integral of e to the u times a negative 1/3, which I'll put out in front, du. And that's going to be negative 1/3 e to the u plus c, which is then negative 1/3 e to the negative x cubed plus c. The plus c is important. So when we integrate this, we end up getting y times e to the negative x cubed is equal to negative 1/3 e to the negative x cubed plus c. And then to solve for y, we divide both sides by e to the negative x cubed. Now, I'm going to think of that, instead of dividing by e to the negative x cubed, as multiplying by e to the positive x cubed. So I'm going to get that y is equal to e to the x cubed times negative 1/3 e to the negative x cubed plus c. And if we multiply that out, can I fit this in down here? Maybe. It's going to look kind of gross. If we multiply this out, e to the x cubed times e to the negative x cubed is just e to the 0, which is 1. Cancels out. So you end up getting y equal to negative 1/3 plus c times e to the x cubed. And look, that's exactly the same as the answer we got last time. Negative 1/3 plus c times e to the x cubed. So it works. And so I should say, if you are able to do it either way, which isn't usually the case, but if you could do it either way, you would still get the same answer whichever way you did it, which is great. So this is the general process for solving a first order linear differential equation. You take your equation, you multiply everything by your integrating factor, and then well, in fact, let's actually write out the process just because I think it's worth seeing. So we're going to write it out very generally, because it's kind of cool to see that no matter what you do, it's always going to work. So let's say we have the following first order linear general differential equation. Y prime plus p of x times y equals q of x. So here's the process. First, well, actually, I should say first, make sure it's in the right format. Make sure we have the above format. We'll start off, we'll have some other examples where we don't start off with that. We have to do a little bit of manipulation first. And then the second thing we're going to do is find the integrating factor. It's going to be mu of x equal to e to the integral of p of x dx. And then multiply both sides by this integrating factor. Or should multiply each piece by this integrating factor. So we're going to get, and I'm going to write this very specifically, y prime times mu of x plus y times mu of x times p of x equal to q of x times mu of x. And I want you to observe something over here. So notably, I want to point out what the derivative of mu of x is. So if I take the derivative of e to the stuff, well, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of mu of x is e to the stuff times the derivative of that stuff. Okay, I'm going to ask you a question. What's the derivative of the antiderivative of p of x? P of x. So the derivative of that is just p of x. So really, if you wanted to, you could say that the derivative of mu of x is mu of x, right? E to the integral of p of x is what mu of x is equal to times p of x. Hey, look, that's exactly what that is right there. So then this left-hand side of this equation is a derivative of a product. This left-hand side, we're going to rewrite the left-hand side as the derivative of a product. And I will point out it's always going to be the derivative of y times your integrating factor. Every single time. So typically my kind of go-to thing that I look for is I just look for y prime times whatever, and I just say, oh, it's just going to be that just without the y prime. It's going to be y instead of y prime, and then it's the derivative of all that. And you can check, right? If you take the derivative of this product, it's the derivative of y times the not derivative of mu plus y times the derivative of mu, which is exactly mu of x and p of x. And that's going to equal q of x times mu of x. Finally, anti-differentiate both sides. So y times the integrating factor is equal to the antiderivative of q of x times mu of x. Now, there's a lot in this step because you actually have to do the integral of q of x times mu of x. And typically, it can be difficult or not. It really kind of depends. And then lastly, you're going to solve for y by saying that y is equal to your integral over there divided by your integrating factor mu of x. Now, don't make the foolish mistake that I used to make when I was taking this, whatever class was covering this material when I was a student. I used to think that the mu of x here and the mu of x here could cancel out, which is totally right. It's totally right. Exactly. You're like, what are you thinking, James? That's totally insane. Right? You cannot cancel this out. You have to multiply q of x times mu of x and anti-differentiate this and then divide by mu of x. So that's kind of something to be aware of. Questions so far? You know, any questions? Oh, no, exactly. All right, it's just me and Reed. All right, so let's look at another example. One that we actually kind of briefly looked at last time, which was, where'd you go? Got things written down here, but let me double check. Yeah. All right, 1 second here. It's a very basic example. I just want to make sure I write it down correctly. Oh my gosh, papers everywhere. Did I write it down? I thought I wrote it down. There we go. Yeah. Oh, yeah. So it's kind of about as basic as it gets. Let's say we want to solve the first order linear differential equation. dy dx is equal to x plus y. I will point out this is definitely not separable. So is a first order linear differential equation. So can we write it as y prime plus a function of x times y equal to a function of x? Yeah, we can. Just be careful. So I usually like to rewrite dy dx as y prime, if that makes sense. So I'm going to write y prime, and I'm going to bring over, well, I have to have the y part come next. I'm going to bring over the y and subtract y and get minus y equal to x. In this particular example, my q of x is the function x, and my p of x is the function -1. It's not very exciting, but as we have, do be careful. If you have y prime minus here, just like in the previous example, we have to think of it really as y prime plus whatever your function of x is times y. Cool. So now we're going to do it. So here's what I'm going to point out. Well, actually, let's do one more thing and then I'll point something out. So our integrating factor here, our mu of x is e to the integral of p of x dx, which is equal to e to the integral of -1, which is just e to the -x. Now, I'm going to mention here that we're going to show the work still, but it's possible that we could just jump to the solution, or at least the step before we integrate. We could totally jump to the fact that our answer, y, is going to equal 1 over the integrating factor times the integral of q of x times the integrating factor mu of x, which in this particular case is 1 divided by e to the -x times the integral of q of x, which is x, times mu of x, which is e to the -x. Depending on what your professor says, you are it's totally fine just to jump to there as soon as you have found the integrating factor. But it's more than likely, actually, I keep getting really blurry over here. I wonder why that is. I mean, it's not that big a deal. It's just curious to me that I keep blurring in and out. Oh well. You're probably going to be asked to show the work where you have to multiply both sides by your integrating factor, rewrite the left-hand side as a product rule derivative, and then integrate both sides to get to this step. So let's do that. So I'm taking this, I'm multiplying everything by e to the -x. So I have y prime times e to the -x plus y times e to the -x times -1 equal to x times e to the -x. I do like, when I rewrite this, when I multiply both sides by the integrating factor, I really do like to write y prime first times whatever your integrating factor is, plus y first times whatever all the other stuff is. It makes it easier for me to see it's a product rule. So then this left-hand side is just going to be the derivative. Now, I'm really just going to look at my y prime, and let's make sure that really looks like a prime there. I'm going to look at my y prime times whatever and just rewrite it without the prime on the y. I'm going to write it as y times e to the -x, the derivative of all of that. And it is. Derivative of y is y prime times e to the -x plus y times the derivative of e to the -x is e to the -x times the derivative of -x, which is -1. Totally works every single time. If you have this format, this process can't fail to produce a result. It might produce something that's not integrable, but it's still going to produce a result. So then we anti-differentiate both sides. The antiderivative of the derivative is just the function. So we get y times e to the -x equal to the antiderivative of x times e to the -x. Now, for the integral of x times e to the -x, that's going to be integration by parts. So let's do that over here. So for the integral of x e to the -x dx, our u is x, our dv is e to the -x dx, our du is 1 times dx, our v is the antiderivative of e to the -x, which is e to the -x divided by -1, which is still like multiplied by -1. And then we plug that all in here. So we end up getting y times e to the -x is equal to, so that's going to be u times v, so -x e to the -x minus the integral of v du. So minus the integral of negative e to the negative x dx. So I see a minus here, so I'm just gonna make those both pluses to make my life easier. And then when I integrate e to the negative x, I get e to the negative x divided by negative 1. So I'm going to get the equal to, if I was doing this, I might actually rewrite the left-hand side as y divided by e to the x, just so it's easier for me to see that I can multiply both sides by e to the x to get my final result. But doing this, I'm going to get y divided by e to the x equal to negative x e to the negative x minus e to the negative x plus c. And then when I multiply everything by e to the x, I'm going to get, I just cost myself some room there, y equal to e to the x times negative x e to the negative x minus e to the negative x plus c. It is okay to leave it in this kind of not multiplied out form, but to me, it seems always better to multiply it out because, I don't know, that's just the way I see it. So if you multiply it out, e to the x times e to the negative x is 1, e to the x times e to the negative x is 1. So you end up with y equal to negative x minus 1 plus c times e to the x. It is really, really important that that constant term shows up because that constant term does get divided by your integrating factor, or I should say, yeah, exactly. Yeah. Questions, comments, observations? All right, let's look at some harder examples. Let's see, where have you gone? 1 second. Yeah, we'll do that, maybe that. Why is everything over the place here? Sorry. There we go. Okay. Lots of examples over here. Cool. Bajillions of pieces of paper. Okay. All right. Got it together here. Those are all separable. I'll take some non-separable ones. So let's look at the following. Sure. Let's try solving the following. X squared times y prime plus 3xy equal to sine of x. So whenever I see something like this, I ask myself, is it separable? Usually, if you can separate the variables first, that is a better choice. Better is maybe, I don't know, a matter of opinion, but it's usually going to be easier to separate variables. You might try that here. So to separate variables, you want to isolate y prime. So I'm going to say, okay, can I separate? So I'm going to have x squared times y prime equal to sine of x minus 3xy. And that's a pretty good indication I'm not going to be able to separate. Because if I actually isolate y prime is going to be sine of x minus 3xy over x squared. And there's no way to get that y over to the left-hand side, really, without also bringing something else along with it, right? I can't factor this y out from that. Now, if there had been a y here, then I totally could separate them. Then I'd be able to factor out the y from the top, bring it over to the bottom, and I probably wouldn't be able to anti-differentiate the right-hand side, but I could still separate them. But it's not separable. It doesn't work. So instead, we're doing the first order linear differential equation thing. But we're going to note that this is not written in the standard way. Whenever you're trying to do first order linear differential equation, you have to write it as just y prime by itself plus a function of x times y equal to a function of x. If it doesn't look like that, you can't do it. So here, what's kind of preventing me from seeing it in the usual way is I have an x squared times y prime. So the first step is going to be divide everything by x squared. Before you start finding the integrating factor. So I'm going to have x squared y prime divided by x squared plus 3xy divided by x squared equal to sine of x divided by x squared, which is going to become y prime plus 3 over x times y equal to sine of x over x squared. Cool. So then we're going to find the integrating factor. I will point out a lot of the time in these first order linear differential equations, you end up getting a p of x that's like 1 over x or 2 over x or 3 over x, which usually makes your integrating factor really, really nice. Because when you find the integrating factor as e to the integral of 3 over x, well, the integral of 1 over x is the natural log of x. So 3 times 1 over x is going to be the integral that's going to be 3 times natural log of x. We definitely ignore the absolute values that we would usually get when we integrate 1 over x. Totally fine. And then this actually does, so first of all, it does simplify, and we should simplify it. So this 3 comes up as the power. We can write this as e to the natural log of x cubed, and then e to the natural log of x cubed is just x cubed. So typically, when your p of x is 1 over x or 2 over x or 5 over x or whatever, something over x, your mu of x is going to be x to a power. In fact, it's going to be x to whatever that coefficient's power is. So like if this was a 5 over x, we would end up getting x to the 5th. If this was a negative 2 over x, we would get x to the negative 2. So it always does simplify when it's that kind of thing, and we should always simplify it. Because multiplying x cubed by sine of x over x squared is going to simplify nicely. Whereas if I left it as e to the 3 natural log of x, that looks way worse. So then do the multiplication. So I'm going to multiply everything by x cubed. So I'm going to have x cubed times y prime plus x cubed times 3 over x times y equal to x cubed times sine of x over x squared. In general, I would probably just do the simplification as I was doing that first step, but I'm kind of writing it out here. So this is going to be x cubed times y prime plus 3x squared times y, and x cubed divided by x squared gives me just an x times sine of x. Great. That left-hand side is for sure the derivative of a product rule. This left-hand side is definitely the derivative of x cubed times y. Always works, right? It's the same story over and over and over again, just different flavors. So we're going to say that x cubed times y is equal to the antiderivative of x times sine of x. And just like in the previous problem, this integral of x times sine of x requires integration by parts. I will remind you that tabular integration is an option. You remember tabular? Okay, so it's not really necessary here, but for tabular integration, so it's just a shortcut for integration by parts. Kind of like how synthetic division is a shortcut for polynomial log division. So if you want to do tabular, it has to be x to a power times sine or cosine or e to the x, because those are the ones that are kind of cyclical. So I could do it tabular by saying my u is going to be x, and then finding all the derivatives. And my dv is going to be sine of x, and then find all the antiderivatives. The antiderivative is negative cosine. The antiderivative is negative sine. And then my antiderivative is going to be plus x times negative cosine x minus 1 times negative sine of x. Usually we use it for ones that require more than one step. Like if this was x cubed times sine of x, you'd have to do integration parts 3 times. So here we're going to get x cubed times y is equal to negative x cosine x plus sine of x plus c. And then finally, we're going to divide both sides by x cubed so that y is equal to, so I'm going to do the math. So x divided by x cubed is going to give me a negative cosine of x divided by x squared plus sine of x divided by x cubed plus c divided by x cubed. That is my general solution. Sure. It's going to throw a particular solution. Yeah, let's do that one next. Cool. Maybe not. Let's see. Sorry, 1 second. Got to think here for a minute. Yeah, okay, fine. Let's look at that. So, questions? I mean, I don't feel like you have questions. Like, someone have some questions. Trying to think if there's anything I want to observe here. No, I don't think so. Let's look at another example. Sure. Let's look at this one. Let's go over here, actually. Yeah, that should be fine. We'll see about this one. Let's try. That's going to be boring. That's fine. It's good. It's good to be boring sometimes. So let's look at this example. Let's say we have xy prime plus 2y equal to x times cosine of x. And we're also given the initial condition that this is where I'm always like, I'm always worried when I'm like dividing by 0 or something. So let's pretend like our initial condition is sure. Y equals 6 when x equals 0. Notably, you could also write this as y of 0 is equal to 6. Okay. Same thing over and over. So first of all, it's not going to be separable. Usually, if someone's writing it in this way, where it's kind of already looking like it's in the usual format for first order, it's probably first order. It doesn't mean it couldn't also be separable. Sometimes they are both. But here we're going to divide everything by x. So we're going to write this as y prime plus 2 over x times y equal to cosine of x. All right, looking good so far. Let's find our integrating factor. Mu of x is going to equal e to the integral of 2 over x dx, which is equal to, if you really like, you can factor out this 2 first just to make it easier to see. 2 times the integral of 1 over x. Then, oh yeah, the integral of 1 over x is natural log of x. I will mention again, really it's the natural log of the absolute value of x, but we really just ignore the absolute value when we're doing the integrating factor. Like it's just, we pretend it's not there. And that's going to be e to the natural log of x squared, right? We're just bringing that 2 up into the power of the logarithm using those logarithm rules. And then that's going to be x squared. So we're going to multiply everything by x squared. So let's see what that gives us. We're going to have x squared times y prime plus x squared times 2 over x will give us a 2x. And then we're going to have x squared times cosine of x. So we're going to rewrite this as the derivative of x squared times y equal to x squared times cosine of x. And then we're going to rewrite that as x squared times y equal to the antiderivative of x squared times cosine of x. And this is a great opportunity to actually use tabular method, because here you would have to do integration by parts twice. So looking at this, I know that my u should be the x squared and my dv should be the cosine x, right? Remember I'll remind everybody of the late acronym. This is how you choose u if you're doing integration by parts. So first you choose a logarithm. Oh, I don't have any logarithms. Then you choose any power of x. Oh, great, I have x squared. So I'm going to choose u equal to x squared. But if you didn't have that, you would choose u equal to a trig thing. And you almost never choose u equal to e to the x. It's like never your choice for u. So here our u would be x squared, our dv would be cosine x. And then we would do integration by parts, and then we'd have to do integration by parts again. Or we can use tabular, where we say, okay, my u is x squared, and then we find all the derivatives of u until you get to 0. That's why it has to be x to a power so that the derivative is eventually 0. So my derivatives are 2x, 2, and 0. And then my dv is going to be cosine x, and then we find all the antiderivatives. So the antiderivative of cosine is sine. The antiderivative of sine of x is negative cosine of x. The antiderivative of negative cosine of x is negative sine of x. And you want to do this so that you have the same number of rows. So you do your u, you go all the way down to 0 for the derivatives, and then you do dv and you do the same number of entries to make sure that the number of entries match up. So just a reminder, this way we are finding derivatives. This way we are finding antiderivatives. Cool. So then, and this pattern always holds, it's this upper left thing, and you go down to the right, and you multiply those together, and you add. So it's plus x squared times sine of x minus 2x times negative cosine of x plus 2 times negative sine of x, always works that way. So this is going to end up giving us x squared times y equal to x squared times sine of x plus 2x times cosine of x minus, yeah, and this is where I knew I was making I was afraid of this. I'm gonna have to change my initial condition. That's all right. Minus 2 times sine of x plus c. So the reason I need to change my initial condition is because I'm going to end up dividing both sides by x squared, which means x couldn't really be 0. Which I guess makes sense if you think about my original equation here. No, it's not. No, never mind. So I'm just going to make a quick, yeah, go ahead.
The last one is negative sine x. Okay, so it's the minus 2 sine of x plus c, right? But it's on the tabular method.
Yeah.
The last sign is negative.
Right. But it's a plus 2 times that.
Oh.
So this plus minus plus all alternates every term. So I'm going to change this initial condition to be y equals 6 when x equals 1 instead of when x equals 0, just so I don't end up dividing by 0. Sorry about that. So solving for y, dividing everything by x squared, we're going to get y equal to sine of x. And 1 is also a bad choice here, but fine. I'm going to change that again. Sorry. Plus 2 cosine of x over x minus 2 sine of x over x squared plus c over x squared. And this problem doesn't really lend itself very well to initial conditions. So maybe we'll just do the initial condition on the next one. It's good. I mean, I should point, you could find C here. It's just going to be awful. If I plug in 6 for y and 1 for x, I'm going to have 6 equal to sine of 1 plus 2 times cosine of 1 over 1 minus 2 times sine of 1 over 1 plus c over 1. It's just like, I mean, it's fine. You'll get c equal to something with sine and cosine of 1 in it, but it's kind of gross. So is there a way I can make it work better? Not really. Yeah. Oh, well. So let's kind of ignore this. All right. Yeah, let's look at one more example that actually does turn out to be kind of all right here. How about that one? That one looks good. Yeah. Except they're all kind of the same variety here. Let's pick something a little bit different. Yeah, sure. Let's try this one. Let's try tangent of x times dy dx plus y equal to sine squared of x. And it's definitely not going to be separable, because if we try bringing the y over here, you're going to get sine squared minus y, and there's no way of factoring out the y or the x from that. So it's definitely first order linear, or at least I should say, if it's going to be either one of them, it can't be separable. So we're going to try and see what's first order linear. It does look first order linear, right? You've got your first derivative, you got your y to the first. It should be first order linear. It is first order linear. So let's do the work. So I'm going to divide everything by tangent of x. Okay. Or maybe I should think of that as really multiplying everything by cotangent of x. So divide by tangent of x, aka multiply by cotangent of x. Or really, aka multiply by cosine of x over sine of x. Might be the way I actually think about that. We'll see. So doing that, my first term is going to be just y prime or dy dx, so I actually divided by tangent. My next term is going to be y times cotangent of x. And my right-hand side is going to be sine squared times cotangent, which is sine squared times cosine over sine. Let's write it as sine squared times cosine over sine. And the next step, we will rewrite this as just sine of x times cosine of x. Okay, so now for the integrating factor. So mu of x is equal to e to the integral of our p of x, which is just cotangent of x. Do we remember what the integral of cotangent is? It's okay if you don't. But it might be easier to see if you write it as cosine over sine. So if I was going to do the integral of cotangent of x dx, that's the integral of cosine x over sine of x. And now how could I try and solve that integral? Right, we're going to let u equal sine of x. du is exactly cosine of x times dx. So this integral becomes the integral of 1 over u du, which is the natural log of the absolute value of u, which is the natural log of the absolute value of sine of x. We're going to ignore the absolute value part, but the rest is good to go. So this is going to equal e to the natural log of sine of x, which is great. It's going to be e to the sine of x. Sorry, not e to the sine of x. E to the natural log of sine of x, which is just the sine of x. Apologies. You will see with a lot of these first order linear differential equations that your integrating factor ends up being e to the natural log of something so that it works out nicely. So then we're going to multiply everything by it. So we're going to get y prime times sine of x plus y times cotangent of x times sine of x equal to sine squared of x. I'm actually not going to cancel the sine here because I'm going to see that the cosine x over sine of x is going to cancel the sine with the sine I'm multiplying by right now. So these sines cancel. And actually here also, right, cotangent again is cosine over sine. So this really ends up being cosine x over sine of x times sine of x, and then the sines cancel to just leave you with a cosine. So this really is y prime times sine of x plus y times cosine of x equal to sine squared x times cosine of x. As is always the case, the left-hand side is going to be the derivative of the product. Just take your y prime thing and drop the prime. So that's going to be the product y times sine of x. It's going to be the derivative of that equal to sine squared x times cosine of x, which means that y times sine of x is going to equal the antiderivative of sine squared x times cosine of x dx. Once again, we're in a u substitution situation. So for this integral here, we're going to let u equal sine of x again, and du is going to be cosine of x dx. So this ends up being the integral of u squared times du, which is u cubed over 3, which is sine cubed x over 3, plus c. So we end up getting y times sine of x equal to sine cubed x over 3 plus c. If we divide everything by sine, we end up getting y equal to sine squared x over 3 plus c divided by sine of x. Or you might write that as c times cosecant of x. Of course, I've run out of room on this page of paper. Let's say we had an initial condition. Let's say we were given the initial condition y of pi over 2 is equal to, I don't know, let's say 4. Find the particular solution. So usually finding the particular solution, once you've done all the other work, is really just kind of a little bit of our algebra and arithmetic. It's not that terrible most of the time. I guess here it's also some trigonometry because you have to plug in pi over 2 to sine. So we're just going to throw this into our formula and say, okay, great. So if we know that y equals sine squared of x divided by 3 plus c over sine of x, well, I'm going to plug in 4 for y and pi over 2 for x. So sine squared of pi over 2, 3 plus c over sine pi over 2. Luckily, the person making up this problem picked a nice value for the angle. Sine of pi over 2 is just 1. So we end up getting 4 equal to 1/3 plus c. So that's going to give us that c is equal to 4 minus 1/3, which is 12/3 minus 1/3, which is 11/3.
To the oversight. Oh,
right. Sine of pi over 2 is just 1. And so then we would go back to the thing you have to remember about the particular solution is you're not done when you find c. We're done when we go back and plug in c to the general solution and write the particular solution. So our particular solution is going to be y equal to sine squared of x over 3 plus 11/3 over sine of x. And if I was trying to write this in a nicer looking way, I would either write this as sine squared of x over 3 plus 11 over 3 sine of x. Or if I was going for a common denominator kind of vibe, I could bring that sign up as cosecant and write this as y equals sine squared of x plus 11 cosecant of x all over 3, if you really wanted to. That doesn't really matter, but it matters a little bit, I guess. I guess it matters in that the thing I always go back to is when you're writing things in different ways, sometimes when people are writing solutions for textbooks, they will write it in a very specific way. And if your answer looks vastly different, it can be hard to tell if you've actually got the same answer or not. So it's good to be able to simplify things reasonably well. All right, that's all I've got. There's a lot. So I've got a few handouts that have some more problems on them. Has he assigned any homework yet? Okay, I'll take a look at that and see how it looks. And then if I feel like you need more practice, I'll probably post more practice anyway. But I think I also did post a link on the modules on the handout section that said like if you want more homework practice or something like that, and it's a link to Dr. Kuba's website from 16C when he taught here he taught here a while ago, but definitely like it's got lots of homework problems from the textbook. So if you're looking for more practice, it's a great place to get more practice. So yeah, if you're looking for more practice, I would go check that out.